Namaskar. So now as we have seen about transpose of matrix, what it is, how to calculate, how to estimate what are the properties. Now let's see associated with that some further properties utilizing the transpose of a matrix. So here we will see that what is symmetric and skew symmetric matrix and their properties. So let's begin. So as we have seen that if there is a matrix the symmetric and skew symmetric matrices are defined for a square matrix. So let's say if there is a square matrix A which is represented as Aij, right, and it have order of m cross m, right, because it should be a square matrix. And then you can have a transpose which will be represented as Aj, which will be again of the same order. Right, so this matrix A would be known as symmetric matrix if A dash is equal to A, right? Then this would be known as a symmetric matrix. So it would mean that you can say that Aij is equal to Aji. So for example you can take a matrix, let's say if it is A is equal to root 3 2 3 2 minus 1 minus 1 3 minus 1 1, right? So if you take A dash, you see if you take A dash means you convert the rows into columns, so you will get 3 2 3 2 minus 1 and 3 minus 1 1, right? See, so you see that there is merely any difference and you get the same value. So it would mean that A dash is equal to A. So it means that A is a symmetric matrix. Now you can have the other case. In that case, let's say if you have a is equal to Aij, it's again a square matrix m cross m. Then if you have A dash represented as minus Aji, it would mean that minus A, you get a negative sign out. In that case, this matrix A is called skew symmetric matrix. Right? So now you can see the very nice important property that if it would mean that Aij is equal to minus Aji, right? So you may have a cases where Ai is equal to minus Aii. It would mean that Aii is equal to 0. So it means that if this is a square matrix, all the diagonal elements of a skew matrix would be 0, because then it will be justified. So an example of skew symmetric matrix, you can have a look. That for example, you would have a matrix B, and obviously you should have all the diagonal elements 0, and this would be let's say this, right? So now you take the B dash, so you'll get you try to get B dash, so you'll get 0 E F minus E 0 G minus F minus G 0, right? So now you see that if you take minus 1 out, so multiply inside with the minus 1, so you will get 0 E F E minus E 0 G minus F minus G 0, right? So you see that this is equal to your B, so it becomes minus B, right? So it means that B dash is equal to minus D. So it means B is a skew symmetric matrix. So there are two important theorems related to that, very nice properties again when we are doing complicated matrix calculations, so they are very useful there. So let's see what are these theorems. So theorem 1, theorem 1 is that for any two matrix, for any square matrix, let's say A, which have a real integer, means A, I, J are the real numbers. In that case, always A plus A dash, the matrix and their transpose of the matrix addition would be a symmetric matrix, right? So you can easily prove that. It will mean that let's say there is a B is equal to A plus A dash, right? So what would be B dash? So B dash would be A plus A dash transpose. Now we know the property. Now A plus B transpose is equal to A transpose plus B transpose. From there you can utilize A transpose plus A transpose, and now we know that transpose of a transpose is the same matrix, so it will be A dash plus A. So as we know that matrix follows the commutative law, so you can write as A plus, right? So you can see that you get the same value is equal to B. So it would mean that transpose of the matrix is getting same matrix, so the addition of that is symmetric matrix. Similarly, it also says that the theorem that if A minus A dash would be a skew symmetric matrix. Skew symmetric matrix, right? So just to prove that, so how will it prove? So let's say again you have a matrix, let's say B, which is written as A. Now instead of plus, now it is having minus, right? So what would be the transpose of that matrix? It would be A minus A dash transpose. Now it would mean you can have the addition of the other two, so it can be A dash plus minus, you can have A dash dash. Now you see this is multiplied by 1, so it will be equal to the individual address, so you can have A dash plus minus 1 into, that is the constant, and A dash half dash, then you can have A dash plus, this is plus and this will become minus, and then A dash becomes A, right? So now if you commutate, so it can be minus A plus A dash, and if you take minus out, then you can write A minus A dash, which is your minus B, right? So you see that if you have a matrix written as the subtraction like a matrix and the transpose of the same matrix, the difference would be a skew symmetric. Right, so this is your first theorem, which says that if the elements are all real numbers, so then the sum of an matrix and its transpose is always a symmetric matrix, and if the sum of difference of the matrix and its with its transpose is always a skew symmetric matrix. So this is theorem 1. Now let's say that what we have in the theorem 2. So theorem 2 is that any square matrix, let's say A, it can be expressed as a sum of symmetric and skew symmetric matrix. So for example, you can write A is equal to half of A plus A dash and half of A minus A dash. So you just saw in the theorem 1 that this A minus A dash is a skew symmetric matrix and A plus A is a symmetric matrix. So you can see that this is a sum of the symmetric and skew symmetric matrix, where you can see that this and the other property AKA dash is equal to KA dash. So it would mean that 1 by 2 A plus A dash is a symmetric, and 1 by 2 A minus A dash is skew symmetric, right? And it means that you can represent any matrix with sum of symmetric and skew symmetric matrices. So these are the some important properties, and the symmetric, skew symmetric, of course if skew symmetric matrix, all the diagonal element will be 0, and you can represent any the sum and sum of the any matrix with its transpose is always a symmetric matrix, and difference is always a skew symmetric matrix. And the other theorem is that you can represent any matrix with in the as a sum of two symmetric and skew symmetric matrix. So that's a really good property. You will see in a later stages when we are talking advanced matrix calculation. So this property will be very useful there. So you solve more problems related to this. There are many examples given and very simple. You can try and you can proceed further on that. So now we'll move further in this and we'll discuss in our next lecture about elementary operation like transformation of a matrix. What are the concepts, some basic understanding about that. So see you there. Thank you.